Welcome, Josh. Thanks for coming. Let me share my screen and I'll talk about the plan today. So today is regression analysis day. So it's kind of an important day in terms of usefulness. Regression analysis is a major piece of statistics. I know we're only spending 1 week on it, but it is a big part of it. And again, this is just the elementary stats class, so we can only spend a little of each week. I mean, a little bit for each thing. So I'll start out as always answering any questions you might have. And I want to let you know, always good to take a look at the calendar. And project 2 is due December 11th. It may seem like a long time from now, but it'll come fast. So that needs to happen, and definitely want to post your project idea on the discussion board, the project 2 discussion board. I'll be, and then I'll take a look at it, let you know, if it's going to work, what little modifications you might want to do, or whatever. And, but definitely you want to be working on that project and moving forward with it. Don't wait till the last minute. That's always a bad idea. So that is project 2, and make sure you have partners, by the way. 3 is best, 2 is okay. So that's the suggestion. One thing is, usually at this point, if someone's still in the class and willing to work with you, they're probably going to stay in the class for 2 more weeks or 3 more weeks because we're almost done. So you usually don't have to worry about any drops or anything, but you want to make sure that your old partners are still in the class if you hadn't contacted them. So that's just a note. Another thing that is, this is week 10. And what's important about the number 10? Hopefully you all know.
An exam.
Yeah, 10 is an even number, and even numbers are exams. So don't forget that you have your week 10 exam that is due as usual by Sunday. Don't wait till the last minute. I recommend getting it done by Saturday. You know what I mean? That way nothing disastrous will happen, or even Friday. So you do have an exam that you'll be working on. We've had kind of a week of rest. Hopefully you did your extra homework, which is to gain weight. That's what you're supposed to do on Thanksgiving. So that was really all you had to do in stats for last week. So hopefully you all had a good break. I ate lots of turkey, and you might have also. So just let you know that that's coming up. We have this week, we'll do regression analysis. Next week is really our last week of regular statistics material, of new material. And it's actually a short chapter. It's chapter 13. So it's actually not that hard a chapter, but you have your project to work on, so that's important. And then the following week, we're actually done on Wednesday. Wednesday will be your week 12 exam will be due then, because then the quarter's over is the idea. Class is over. So we're almost done. We're almost done. And as I've always mentioned, I'm always happy to help you out with whatever, whatever you need in terms of stuff. You're always welcome to post on the Q&A board or ask me questions, ask here. And Braulio also is happy to help out. So are there any questions about anything? Any questions? I'll be happy to answer. I know you might have been thinking about Thanksgiving for a week and not even thinking about stats, but it's time to get back into it. Any questions? Okay, if there's no questions, I want to mention kind of the whole main idea of what we're doing today, okay, and this week. So the idea is we're going to be doing regression analysis, which is a huge topic. And I want to mention a few things. One is we're only doing what's called linear regression analysis with just one and a single independent variable. So I want to give you a heads up when you're looking at the discussion post assignment, for example. Make sure that you don't, first thing is it needs to be an article that's not a statistics article. It should be an article about something else, just like all the others. And the second is make sure that it is just linear regression analysis with one independent variable. Okay. A lot of people make the mistake. They see the word regression, they say it must work, but there's a lot more advanced stuff that we don't do in this class. And I want you to make sure that you don't post something that is one of those advanced things like multiple regression or like, nonlinear regression analysis. Make sure it is exactly what we're doing, if that makes sense. And by the end of this lecture, hopefully you'll really have an idea of what I'm talking about. So what we're going to be looking at, we're going back to quantitative variables, but we're doing it with a different point of view. We had done a difference between two means in chapter 10, okay, 2 chapters ago, and that's what your project's on, by the way. This is not about the difference between two means. What this is about is you have two quantitative variables, and you're going to use the outcome of one of the variables to possibly help you predict the other variable, which is very different than saying, do they subtract to 0? It's not about that. It's about prediction. And it's about looking for trends, saying, hey, if this one goes up, do I predict the other one is going to go up? Or maybe I predict the other one is going to go down. And in what we're going to be doing is in a linear fashion. Okay. Or maybe I look at one, I see it goes up, and I realize they have nothing to do with each other, and I can't make any predictions. And that happens too. So regression analysis is all about that. And in particular, which I don't want to spend all the time drawing one, you could plot the points. So hopefully you all know how to plot points on an XY axis. If you have two variables, right? If you have two numbers, you can put the first comma, the second, and plot it. And you can plot a whole bunch of them. Okay. And we're going to see that in a bit. I'm going to give you an example that's very important to Tahoe. Sorry if you're not from Tahoe, but you'll still understand it, even if you're not from Tahoe. It's the most important example. And it's my favorite linear regression example ever that's ever happened because it was super important for our particular town. So we're going to be looking at scatter plots. Then we're going to be looking at something called R. And you may not know the letter R as in what it means mathematically, but you've probably heard the word correlation. So R stands for the correlation. Okay. Unfortunately, they didn't use the word C. I'm not sure why. I think for R for regression analysis is probably what it is, maybe, but I'm not even sure about that. But R is the correlation between the two variables. So it's kind of how much it's linearly it's going to help you to know one to predict the other is kind of the idea of R. Okay, and we'll talk about that. The math, by the way, is way too hard. So all we'll do is look at the number and interpret the number. We're not going to even think about how you actually arrive at the number mathematically. That's my job. Then we're going to look at R squared, and you may say that's kind of silly because you just square R and that's it. But actually it has a special meaning, and it helps you get interpretations if you know what the square of R is. So it has its own meaning. Then we're going to look at the equation of the regression line, and you've probably heard of a regression line. I'm sure, or I shouldn't say I'm sure, but most likely none of you know how to actually calculate a regression line by hand. But you might be able to look at a bunch of points and kind of visually get an idea of what line might be a good fit for those points. They may not, the line doesn't go through every point, but maybe it'll get close to them. And that's the idea of the regression line. And then something that happened in algebra is that you learned, hopefully you remember, what is the standard equation of a line that you learn when you're in maybe 8th grade or something like that? Who remembers me? Pop in the chat box. And hopefully you all learned it. It's very standard, nothing fancy or anything. You remember? It's a standard equation of a line that everyone knows. Ax plus by equals c, that's an equation. Y equals mx plus b is more common. That's what most people think about the equation of a line. Y equals mx plus b. Okay. And hopefully you remember that m is the slope. And there's a good guess that none of you know why they use the letter m for slope. I don't know. Usually no one knows. It's because the French got to it first. And that's the word for slope in French. And you might know mountain or mount, and that's the slope. That's a slope thing. And it's montre. Starts with an M. So that's why it's y equals mx plus b. And b is just because that's the second letter on the, that you've listed, I think is why they call it b. But m actually has a reason. So y equals mx plus b, we're going to be looking at the slope, and we're going to interpret the slope of the regression line. We're going to say, what does it tell you about the prediction? And we're also going to look at the y-intercept, the b, and we're going to say, what does the b tell you about the prediction? Or maybe it tells you nothing. The slope will tell you something, but the b may not tell you anything. So that's important. That's going to be the equation of the regression line. And then a big deal is avoid causation. It's a really common mistake that people make. And that is, if you happen to have a linear regression and you have, a good fitting line, between the two things, then that does not mean that one causes the other. So we have to be very careful with the language. And in fact, the word cause, be careful in anything you do in statistics. It's very difficult to show causation in statistics. And that includes your projects, by the way. Okay, if your p-value is 0.0001, you still shouldn't use the word cause. That's why you use statistically significant evidence kind of stuff. Okay, but not cause. So we're going to avoid words that involve causation, and we'll talk about the language you should use. Okay, and then as I promised you a few weeks ago, every week we're going to do hypothesis testing. So we're going to have a hypothesis test. And anyone know how to pronounce this letter right here? It's not P, by the way. It's a Greek letter. Okay, and let's see, y'all jumping in. Okay, the way you read this is row, like row, row, row your boat. And that's the Greek letter for R, actually. And it kind of looks like a P, it's a little curvier. But that's the Greek letter, and we're going to do a hypothesis test, and that'll be the population R instead of a sample R is the idea. And that hypothesis test basically is you're going to say, is there statistically significant evidence to say that there is a correlation between the two? Okay, or maybe you don't have evidence to say there's a correlation. And that's what we're going to be looking at. And it turns out that if you don't have evidence for a correlation, you shouldn't use regression analysis at all. Okay, not linear regression analysis. You should basically not do it. Okay, so at that point, after doing the hypothesis test, if you get too big a p-value, you say, there's nothing I can say. And that's about it. So that is the plan for today. And I want to ask you, are there any questions about anything? Great time to ask. Any questions? Okay, if there's no questions, then I think I'll move on. And by the way, we don't have like a project to talk about or anything like that. So we may not go that long today. It might be a little shorter than usual, but there's always stuff to say. You know how that is. So just let you know, give you a heads up. It's not going to be a 2-hour type of webinar, but might be an hour, 15 minutes or something. Okay, so what we have is a couple things. I want to talk about R and R squared in general, and then we'll do some. That's the idea. So it turns out that R is the correlation. That's something I mentioned a bit ago. So R is called the correlation. So there's lots of examples that have a correlation. Okay, so for example, if you look at, and I'll tell you, I was just on the phone with a medical telehealth medical thing, and there is a correlation between cholesterol, okay, HDL cholesterol in particular, and how long someone lives. Okay, so you've probably heard of that before. If you have a high cholesterol, then you have a higher chance of having a health issue and possibly dying. Does that make sense? Okay, there's a correlation. Okay, that does not necessarily mean that cholesterol causes death. Okay, there's a whole lot more research you have to do to come up with that idea. That's called biology that you have to do after that. But at least you can look and find a correlation. Okay, there's also, let's say, a correlation between, let's say in elementary school, is a correlation between height and weight. So if I tell you that there's a kid in, sixth grade, there's a kid in elementary school that, is 5 feet tall, then you're going to probably not think that they're, a small weighted elementary school kid. Okay. Because they're probably in 5th grade and not kindergarten. Does that make sense? You don't know for sure. It's just a prediction, and a correlation tells you have a prediction. You could have a correlation at which if something is high, then you predict that the other variable will be high also, like height and weight. If you have a lot of height, then you predict that you will weigh more as your child, if you're a child, right? And then R will be positive, close to 1, like maybe 0.9. On the other hand, there are other things where if you have something that's increased, you might expect something else to be decreased. Does that make sense? So for example, if you look at, say, someone who increases the amount of time they spend sitting around doing nothing, then you would expect that the amount of money they have in the bank might be decreased because they're probably not working much. Does that make sense? Okay, now it doesn't mean that it's a causation thing, but people who are not sitting around at home all day long tend to make more money. Does that make sense? Okay, it doesn't mean that sitting around at home causes you to make less money. It just means that there's this tendency. And then you would have an R that was closer to -1, like -0.9. On the other hand, R could be 0. Okay, or really close to 0. Okay, and there's lots of examples on that. Let's suppose you looked at the temperature. Let's say the high temperature that day in Lake Tahoe. And how about the score of the total number of points in the soccer game in Australia at a high school that you're interested in? In that case, you would guess that R might be 0 or close to 0, because knowing the temperature in Tahoe, do you think that's going to help you at all in how many points are scored in a soccer game in Australia? No, right? They have nothing to do with each other. Do you see that? So then you would probably have an R really close to 0. So typically, if there's very little relationship between the two, then you're going to see R close to 0. Whereas if you have a strong relationship where one predicts high other, if one is high, then the other is predicted high, then it'll be close to 1. If one is low and the other is predicted low, then it'll be close to negative. And one is high and the other is predicted at a low, then it'll be -1 or close to -1. R can never be bigger than 1, and it can never be smaller than -1. So it's always between those numbers. Any questions on that idea? Okay, in terms of scatter plots, if you looked at the kind of the graph, then if the points look really close to being on a line that's positively sloped, you'll have an R that's close to 1. If they're on a close to a line that's negatively sloped, you'll have an R close to -1. If the lines are all over the place, I mean, the points are all over the place, like looking at the night sky is what I like to say, then your R will be close to 0. Okay. There are some exceptions too. I'm just not going to get there now. Any questions on R? Okay, then comes R squared. R squared is the square of R. Turns out when I took advanced statistics, my professor gave an entire 2-hour lecture on why R squared is the square of R. I know that sounds really weird, but it's very deep, but I can't get into the depth. But the good news is if you know R, you can get R squared really easy. You just square it. Okay. If you know R squared, you may not be able to get R because you can take the square root, but it might be negative. And you don't know if it's positive or negative. So you can go one way or not the other. Okay. And the idea with R squared, one thing is I like to take R squared, turn it into a percent instead of a decimal. So if say R squared was 0.2873, then I would like maybe round it to the nearest whole number percent. And I'd say it's 29%. And what it tells you is there's kind of 2 variables. Okay, we're always looking at 2 variables for regression analysis. And the idea is, let me give you kind of an example. Let's say the first variable was the amount of time that statistics students spend with Braulio. And the second variable is their score in the class, their percent score, their total percent course grade, okay, as a percent. All right. And R squared in that case might be something like 0.9. Okay. So what that would tell you is that if you just looked at all of the scores or the percents in statistics for all of the students, then there's a pretty big variation from one student to another. Do you agree? They're all over the place. There's some students that are really low, some students are really high, some in the middle. They're all over the place. Okay. And you can think about variation as a standard deviation. You can have a high standard deviation. On the other hand, if let's say you looked at the groups of students that all spends the same amount of time working with Braulio, the tutor, then the variation in scores for those students that all spend the same amount of time with the tutor is probably going to be much smaller, in particular 90% smaller on average than the variation if you don't just focus on that one group, on the groups. So those who don't spend any time are probably going to do worse. And, some might do better, but a lot of them are going to do worse. And you're going to have a smaller standard deviation because they're all going to be on that low side. On the other hand, those who spend a lot of time getting help with the tutor are probably going to be on the high percents, like in the 90s. They won't all be at, 92. Some might be at 87, some might be at 98. But they're not going to be as varied. They're not going to has a high standard deviation as the group, as everyone total. And that standard deviation is on average reduced by R squared percent. Any questions on that idea? So I kind of want to go over some of the main points. Any questions? Okay, so then comes, again, I'm going over the ideas and then we'll do an example, by the way. We'll do one example. We're going to go through the whole thing. Okay. You have a regression line, and that's like the best fitting line. The math is way too hard for me to explain how to get that best fitting line other than go to the computer, it'll give it to you. That's the best fitting line. The slope of a line, hopefully you remember, is rise over run. Y'all remember that kind of little poem, rise over run, if it's a poem. And the rise is how much y changes, The run is how much X changes. And the easiest is to think about X changing by 1, because then you can take your rise or run, right? It's going to be a decimal when you use a computer. And if the decimal is like, 0.42, then you can write that as 0.42 over 1 and say that X is increased by 1, then Y is predicted to increase by 0.4, by whatever that slope is. That's the idea of the slope. Okay, I'm going through some math, and then we'll have a long example where we do all this stuff. But I want to kind of give you general first, and then we'll do an example. Okay, then there's the y-intercept. The y-intercept, that was the b. In statistics, though, they instead of mx plus b, and you just got to go with it, they often use a plus bx. So be ready for that. So they don't always use those letters for stats. And all I can tell you is just live with it. There are some mathematical reasons I can't go there. Okay. But the y-intercept, what you do need to know is the value of X at the y-intercept is always 0. That's what it means to be a y-intercept. Okay. Sometimes it'll have no meaning at all because X equals 0 has no relevance. So for example, if we looked at age of college students versus GPA, and let's say the y-intercept was 0.3. Why does anyone know why that has no meaning?
Are you asking if r equals 0.3?
No, not R. That'd be the y-intercept. So that's like B. If the y-intercept was point B, and we're looking at age of college students for the independent variable, the X value, and we're looking at GPA for the Y variable, then why would a y-intercept of 0.3 have no meaning at all? No practical meaning. Anyone come up with it? As soon as I tell you, it'll be really obvious. Okay, it's not because the y-intercept is low, actually. It's right here. X equals 0. I told you age of college students. So that would say that it would give you a prediction for a 0-year-old college student. How many college students are newborns? Are less than a day old? It can't happen. Does that make sense? So that would be a way it has no relevance because a college student can't be 0 years old, right? Because that means they were like immediately born. And you can't be in college, by the way. You're usually at the hospital. Being born. Does that make sense? Is that clear? Okay, so it's not the y value that has no relevance there. Sometimes the y value has no relevance. Here it's the x value because you can't have a 0-year-old college student. So just let you know there's a lot of reasons why there's no relevance for y-intercept. One is that the x equals 0 doesn't have meaning, can't happen. Another might be the y can't happen. 0.3 can happen. You can have a GPA of 0.3. I mean, you're a bad failure, but you can have it. But you can't be a 0-year-old college student. Hopefully you know that. Another is that if the values of X are nowhere near, the values of X in the data set are nowhere near 0, if they're all kind of clustered around something like 100 and 0 is nowhere near 0, they're all within, say, 90 and 100, then it also doesn't have meaning. You don't try and make a prediction when it's so far away from everything. Any questions on that? Okay, on the other hand, sometimes it does have meaning. Okay, so instead of the GPA thing, if we looked at the example where I was talking about number of hours a week that you spend working with the tutor versus your grade in the class or your percent in the class, that has a lot of meaning. Because are there people that never go to a tutor? Or that never go meet up with a tutor? What do you think? does that happen? Any thoughts? I wish it was not much. For all of you, probably wish it was not much also. But no, there's a lot of students that never go see a tutor. The thing is, usually the students that are going and actually logging into the webinar, they're the ones that go see the tutor a lot. So you may not even know. But let me put it this way: there's a lot of students that don't get the help they need when they need it. Okay, I wish they all did. Okay, any questions on that? Okay, so that's the y-intercept. So I want to do an example. And in my opinion, this is the biggest and most important example of any example that has ever happened in Tahoe, of anything in statistics, not just regression analysis. I'm going to open this up. Anyone know? Most important thing that statistics-wise that's happened here? I know a lot of you aren't from Tahoe, but you still might know. Give you a few seconds. The new water snow, kind of, but not snow. Something to do with water. So let me tell you, because you don't live here, so my guess is you don't live here. If you lived here, you'd probably know. And that's Lake Clarity. So what we want to make sure, if you haven't been to Tahoe, please go to Tahoe because it's beautiful. Nothing to do about this class. It's just a beautiful place to go. If you've been to Tahoe, you know we have a beautiful lake. Okay, beautiful blue lake. In fact, I did a hike yesterday. It was amazing. So clear, you can see deep down. And we want to make sure that depth of clarity doesn't go away. Does that make sense? We do not want a murky lake. So it turns out there was research done every year. UC Davis tested and looked to see how deep they could see what's called a Siki dish, which is like a little plate that they drop down into the lake, and they keep dropping it down until they can't see it anymore. And that moment at which it loses its sight, then that's called the depth of clarity. Does that make sense? And they have been doing this since the 60s, 1960s. And I will let you know, way back when, like talking almost 30 years ago, the president of the United States came to Tahoe. It's kind of cool. Okay. It was actually President Clinton. Okay. Some of you probably weren't even born yet, possibly, but hopefully you know there was such a president. And he came to Tahoe. And the funny thing is, one of my students was there with him. Lucky person, it'd be cool to like be there when he was being shown this picture. My student was there actually serving him his dinner for lunch. Actually, I think it was lunch, not dinner. And kind of talked about this. So I actually got to hear, I guess, called secondhand. And they collected data every year. And I want to let you know a few things. One is these numbers, let me show you. There we go. This 68, 69, 70, 71, those are the years. Okay. And when I say these years, that means since 1900. It's just too much typing to type in 1968, 1969, 1970. So that's what these are. Whereas these numbers, 31.2, that was the depth of clarity. So that means that, and this is meters, by the way. Scientists tend to use meters. That means that in 1968, they were able to see 31.2 meters in depth. When they drop that dish down, they can drop it and see it that low. I mean, that's really deep. That's like close to 100 feet down, and they can still see it. Our lake's very deep, by the way, if you don't know our lake. Any questions on that idea? Okay. And then they did it in 1969. And they were able to see 28.6 meters. And they did it every year. Okay, all the way to 1999. And they were able to see 21 meters. And by the way, 21 meters is not as good as seeing 31.2 meters in terms of clarity. And this looks a little weird because this is called a scatter plot, which is a graph of the XY axes. But I want to give you a heads up for this particular example, it's kind of off. If you look at the Y coordinates, 35, 30, 25, 20, 15, when you go up, the numbers go down. Okay, that's not normal, but that's what they did so they can show this picture of depth. So you may think that the slope of the line would be positive, but it's actually negative, even though it looks like it's going up, because remember, 35 to 15 is downwards when you're going that way. Okay, and that's not a stats thing, that's just this example. Okay, so the good news is that President Clinton understood statistics. So instead of looking at this and saying, I have no idea what you're talking about, I don't even understand this graph, Clinton actually understood and could look at this and say, we have a trend that doesn't look that good because our clarity is going worse and worse and worse. Any questions on that? Okay, another thing, and this is like, I smiled so much when I heard this. I got to talk to the person in charge of this data collection from UC Davis. And what he said, because I asked him, you know, in terms of these numbers, like this number 31.2, what does that really mean? Was that just one measurement? And I asked him, he said, no, this is, you know, an average of multiple measurements. That's what I was hoping for. And now, remember, I told you I smiled and smiled and smiled. So I asked him, how many measurements do they take to get that average? Any guess on how many they took each year? This is what he told me, and he did not take my class. But he did take stats. Any guess on how many? Yep, 31. Now you see why I smiled so much? So he did his job and made sure that the sampling distribution for every measurement was following an approximate normal distribution. And you actually need that to be able to do good statistics. Hopefully you're there when you have quantitative data, you better have over 30. And 31 is good enough. Any questions on that? Okay, so now what I'm going to do is I'm going to show you, let's see how we can take that data and we can get all of those numbers, R and R squared and the slope and the y-intercept, all the different things we want. So the first thing I'm going to do, and I'm going to copy this. And actually what I did is I took this chart and I typed out all the numbers for all these things to make it easier so we don't have to spend all day watching me like type it one at a time. And I'm going to go to the list of calculators. Any guess on which one I'm doing? What calculator number? Yep, 24. So you should smile a bit because there's only 25 total, which means we're doing one next week and we're done. Next week we'll do ANOVA, but we're on 24. So we're the second to last piece of stats. You could do it one at a time, but I made it so, and actually a student asked me if I could do this because it was too much work to type it in one point at a time. So if you ask me to do something, I can program it usually. And I programmed it so that it actually was much faster, especially with copy paste. And I'm going to do the same thing for these guys. And copy. And then I'm going to paste in the Y variable. Okay, and you have to decide, by the way, which is the X and which is the Y. And the idea is that you're using one of the numbers to predict the other, or one variable to predict the other. That's what you're hoping for. So we're going to try and predict lake clarity given what year it is. Okay. Whereas you probably wouldn't be that interested in trying to predict a year if you know the lake clarity, because we know what year it is. But we might want to predict lake clarity given the year. Any questions on that so far? Okay, so once I get those numbers in, and notice, by the way, they're separated by commas. Hopefully you're used to that. I hit plot points. Okay, and this will actually give you the scatter plot. And you'll notice that it actually does look like a negative slope. So this one doesn't have some fancy looking thing. So the depth looks, higher depth is lower. This just shows you the math. And do you all see the scatter plot? Okay, it also shows you the line of best fit, which is often called the linear regression line, like that. Any questions on the picture? Do you see a trend? Are these points all over the place? Or do you see that there's been a trend over the years? What do you think? Do you see a trend? Yeah, definitely looks like a trend. By the way, is this a good thing? Do we want this trend to happen for our lake? Are we happy? Are we saying we're going to hope this continues forever? Yeah, no, this is a disaster. Because what this says is that you used to have this clarity, you used to be able to see really deep, and it used to be beautifully deep. And then in 1996, by then, in the 1990s, all of a sudden it's kind of getting murkier. Do you see? So it doesn't look good. Any questions on that? Okay, then what we can do is we can look at the numbers. And I want to show you a bunch of things. Here is a regression equation. So y is equal to, and I'm just going to do approximate, 42 minus 0.28x. Any questions on that equation? Okay. Then we also have r. R is negative 0.9 about. And r squared is about 0.84. Any questions on that? Okay. I'm not going to do this immediately, but there's a test statistic and there's a p-value. And it turns out the test statistic is the same t that we had in chapters 9 and 10. It's that same distribution. Kind of looks somewhat normal, but not quite. Okay, and we have a p-value. By the way, is a p-value 2.56? Is that what the p-value is? Is that our p-value, or 2.5, about 2.56? Is that approximately p-value? No, it's nowhere near the p-value. P-values can never be 2.56. What am I missing? Yeah, the E-13. And by the way, if you did this on your smartphone, because smartphones are much smaller, you may only see what's highlighted here, and you may not even see the E-13, and you're going to have to scroll until you can find it. Just a warning that for smartphones, sometimes you can't see this last bit, so you have to scroll a bit. That has to do with, how big your screen is. Any questions on that? Okay, so that's the main stuff we're going to need. So now let's start interpreting. So let's go r equals negative 0.9. Let's kind of do one of these things at a time. Actually, I'll do it in the order I have it here. Let's do our slope. What's the slope? What's the slope of the regression line? Yeah, negative point. I'm going to go negative 0.28. That's probably enough. So our slope is, remember, that's the number in front of the x. So negative 0.28 about. Okay, so that means we could say the rise is negative 0.28 and the run is 1. And notice the rise, that's a change in y, right? And y is the clarity, how deep you can see that dish as you drop it down. So the rise means a drop in clarity or depth of clarity. Whereas the run, that's the x coordinate change. And that's going to be the change. X is going to be the years. So that's going to be year change. Any questions on that idea? So now we can interpret the slope. So what we're going to say is that for every 1 year that goes by, that's the run equals 1, x changed by 1. There tends to be, on average, a decline in late clarity by 0.28 meters. And by the way, if I use the word decline, I don't have to use the word negative. And if you're going to do it in words, usually don't use negatives. You turn it into words, and decline makes it a negative. So let me ask you, are there any questions? Any questions on this interpretation? Any questions on how I arrived at that sentence? Because you're going to be asked to do that. Okay, I mean, not for late clarity, but for something else on the exam, and it's all randomized, so you never know what you're going to get asked. I don't even know. But you're going to ask to have to do something like that also and type something out. Any questions on how I came up with that sentence? I want to mention something very important, tends to be. Okay. That's important. This is only sometimes it happens, sometimes it doesn't. It's also on average. It's an average change. It's not the change, because if we go to this graph again, then some years, like from here to here, there was a big drop in clarity, right? But then the next year, clarity got better. Or I'm sorry, for this one, it was a rise. Yeah, a drop in clarity. And then the next year, clarity got better. Do you see? The next year, it was a big drop. And then it got much better. And then another big drop. Do you see how that works? So it's all over the place in terms of up and down. But if you look at the average change each year, then on average, we see a tendency of 0.28 meters of decline in clarity. Any questions on this? Okay, so very important. Let's go to interpret the y-intercept or explain why it's not useful. Okay. So let's do that. And I'm going to go over the y-intercept. Hopefully you can tell me, what is the y-intercept? Maybe nearest whole number might be good enough. Yeah, 48. So it's important you know how to read the equation of a line. That's the number that doesn't have the x. So 48, ran in the nearest whole number, is the y-intercept. Okay, so now what we need to do is interpret it. So remember, it might help that that means x is equal to 0, y equals 48. Remember, x is the year. And the year 0 means 1900. Any questions on that? And 48 is the meters in clarity. So sometimes it helps to kind of slowly interpret and then get to the sentence. So write down what the y-intercept is, write down what x is, write down what y is, then write down what x is in words, then write down what y is in words, and then use a sentence. Okay. So what we can say is that the best prediction for the depth of clarity in the year 1900, because remember 0 corresponds to 1900 for this example, is 48 meters. However, since none of the data points are anywhere near 1900, right? Because if you look at the data, 1968 is when they started looking at it. Okay, so that's like ages ago compared. Does that make sense? It's not a very good prediction. So are any questions about this interpretation of the y-intercept, or in this case, it's not that useful? Any questions? Okay, I do want to give you the big warning, and I've given this before. It's a lot easier to watch me do it than to do it yourself. Okay, at least most people feel that way. Any questions at all? All right, so now, what is the best prediction for lake clarity today? How do we do that? It's actually not that hard. Any ideas? Might help to look at this. How do we get the best prediction for lake clarity today? Very close. So the idea was set x equal to 2022, except x is a year since 1900. So we're going to set x equal to 122. Does that make sense? That's just what these numbers are. This 69, this 68 is not the year 68. This is the year 1968. So we're in the year, we're 122 years after 1900. So we're going to take that x and we're going to make it 122. So I think the easiest to do in terms of the computer is I'm going to copy that. I'm going to paste right in there. Go times 122. Any questions so far? Maybe not plus minus because that may cause Google problems. I'm going to write a minus. Copy that. And then 14.0677, about 14. Okay, so the best prediction is about 14. Is that good, by the way? Are we happy? Would we be happy if we had a 14-meter clarity? No, it would be horrible. This lake would not look pretty anymore. Okay, so any guess on what President Clinton did? And there were some senators there too, by the way. There's some Congress people at the meeting watching the UC Davis people show what was going on. Any guess on what they did? What the Senate and the president did? Yep, they passed legislation. They put in literally hundreds of millions of dollars to solve the problem. Okay, and I'll show you in a little bit kind of the result. But the good news is, and I think, of course, I'm very biased, but I think that should be a requirement of every president of the United States should understand statistics. You may laugh at that, but I think that's important. Statistics is so important that I think every president should understand statistics. And fortunately, Clinton did. Not all of our presidents have understood statistics, but he was one that did. Okay. So now let's interpret R squared. So again, R squared. I'm going to go to the nearest whole number percent, which is 84%. So here's how we interpret it. We can say is there has been a lot of variation in lake clarity. Okay, and maybe depth of lake clarity. Over the many years before now. But if we just look at groups of years all near each other, okay, in time, then the variation for these groups on average will be decreased by 84%. Okay, another thing to say is that 84% of the variation in lake clarity can be explained by knowing the year. And the other 16% is due to other factors. That cannot be explained by the year. Any questions? Any questions on that? Okay, what are the factors you think there might be? There's not a math question, but it kind of helps to see what I mean by other factors. What are the factors besides just what year it is?
I would imagine like the time of year that you take the sample or like the weather of the day would influence your measurement.
Yeah, let me give you a little better than that. Because remember, I told you that these numbers are averages over lots of different days. So it's really not the time of day you measure because they measured in lots of times throughout and they took an average. It's more of the weather that year. And it's how much precipitation there was that year. So for example, I don't know if you guys know, do you know what California was like in the year 2022 or has been like in terms of weather and particular the amount of precipitation? I think all of you live in California, right?
I think I've just noticed that it's been a little bit colder than usual. Just
Yeah, but
in,
how about precip? How about precipitation over the last since the beginning of the year? And we're already November, so we've got 11 months to look at.
actually not sure.
Okay, we're at like almost record low amount of precipitation. We had almost no precip last January, February, March and that's when we have most of our precip in Tahoe and all of California, especially in Tahoe area, but Bay Area too. So we've had very little precip, which turns out to be really good for lake clarity. So lake clarity was good this year. Does that make sense? So there are lots of causes of changes in lake clarity. And the idea is knowing one of them and it's not the year caused it, but the kind of the population growth is what really caused it, which increased over the years and the amount of cars that came up, stuff like that, all kinds of other stuff. And that was what was killing our lake. But also weather would change and destroy the lake or be great for the lake. Okay, in particular, precipitation. Okay, and again, I've looked at all the data, so you can trust me on that. So, but 84% of the variation can be explained by knowing what year it is. And that's most of it. But then some of it's due to other things like weather. Okay, like whether you're in a drought year or a heavy precip year is the main thing. Any questions? Any questions on that? Okay, so we've already done the slope and y-intercept. Let me erase this. And we've done this. Okay, and just kind of a note, the y variable has a standard deviation that'd be quite large, but if we only focus on y variables that correspond to a fixed value of x, then the standard deviation of the variation is decreased by that r squared of that percent. Okay, that's kind of in general. It's good to know the general, but it's good to have an example too. Any questions on that so far? By the way, r was negative 0.9. Which is close to -1. This tells us that there is a strong negative correlation between year and lake clarity. Okay, so one thing R gives you that you can't get from R squared is the fact that it's negative. We know it's a negative correlation. So as the years progress, the lake clarity tends to decline. Any questions on that? Okay, I want to mention something that notice R is negative and notice our slope was negative. I want to let you know that the slope and the sign of the slope and the sign of r will always be the same. So if the slope is negative, then r is negative. If the slope is positive, r is positive. If the slope is 0, r is 0. The numbers won't be the same. 0.28 and 0.9 are not the same number, but the sign will always be the same. Any questions on that? Because the slope tells you as one goes up, does the other go up or down and how much? And the correlation also says as one goes up, does the other go up and down? Okay. Any questions so far? All right. Is this, I mean, we did all this interpretation stuff. I did tell you that they looked at these data values. These are averages. So we have a large enough sample size. But is this trustworthy? And the way you decide if it's trustworthy is you do a big hypothesis test. And I want to let you know, in our class, we're gonna do this one. H naught rho equals 0. HA, and something's called H1, by the way, rho not equals 0. So we're going to do a hypothesis test to see, is there a correlation? And if there is a correlation, then that correlation is not 0. If there's no correlation, the correlation equals 0. Any questions on that? So the good news is the null and alternative hypothesis for this chapter are always exactly the same. Okay, whereas the last chapter, they're all over the place, right? You had big sentences you had to do and all kinds of stuff. But here, it's just rho equals 0, rho not equals 0, period.
So we will not be using the bottom two options?
No, I decided that I can only do so much in our class. I will let you know that people do use the other options sometimes, not as often, but I can only do so much. Sound good? Okay, just like no way would I ever have you tell me how to, calculate the p-value or t or r squared or this, slope and y-intercept, all that stuff I would never have you do in this class other than click plot points. That I don't feel guilty if I tell you need to know how to click the plot point button. Sound good? So I can only ask you to do so much. So we're gonna only, at least for the main stuff we do, it's equal 0, not equal 0. Okay, and it's always rho. Okay. So we have H naught rho equals 0, H1 rho not equals 0. The p-value is very small. That was 0. I forgot how many zeros there were, but it was a hell of a lot of them. Yeah, 12 zeros before the 256. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 2, 5, 6. Tiny, tiny p-value. Okay, so you should all know the first few words that I need to put out because it's always the same for hypothesis testing. When you have a p of really close to 0, what are the first few words you write down? Let's see if you can put them in the chat box. Again, you should all know the words. Yep, there is statistically strong evidence. I'm going to write strong, statistically significant evidence. And in fact, this is so close to 0, I'm going to even really exaggerate and really be proud and say very strong statistically significant evidence because I'm really low. If it's lower than 0.01, I'll use the word strong. If it's like obscenely low, I'll use very strong typically. To conclude, that, and now we could say there is a correlation between the year and the depth of lake clarity. Any questions on the hypotheses? Okay, so that means that all of the stuff we wrote down is useful. Okay, it's worthy. Whereas if the p-value was say 0.3, then everything here would be a waste of time and wouldn't be trustworthy at all. Any questions on that? And it could either be because there's really no correlation, or it could be your sample size is too small and you're used to that. Those are issues for p when you have a high p-value. The two possibilities: sample size too small, or it just wasn't right. Any questions at all on this example?
I guess I have a question regarding regressive analysis in general, which is, when do we know that doing regressive analysis will be helpful to us or meaningful in some way? Because in this case, it was helpful because it identified that there was, in fact, a problem, a trend, but it might not have told us like what to do about it, for example. Like, it might not have informed the exact policy they passed. So how do we know that it like is worth using?
Right. So here's my strong suggestion, and that is work as a team. And what you want to do is you want to make sure there are statistics people, statisticians, and also there are environmental engineers. Okay, so the idea is that you have the data collection, you make sure that the statistics are done right, that people who understand statistics can do the statistics. And then when you find out that you did have a correlation, then you talk to the engineers, the environmental engineers, and say, can you see anything that might be a reason for this going on? Do you see? Because the year itself is not what's causing it. It's people that are causing it. Does that make sense?
Right. I guess also part of that
and you need environmental engineers, right? If you don't have environmental engineers, then you have no idea how to fix the problem.
Right. I guess part of like a sort of tangent question is, how do we know that past historical results will in any way signify future results? Because I guess it's like sort of the stock market, like people base their models off of what happened in the past, but we don't necessarily know what's going to happen in the future because it's like, it's dynamic. It's not necessarily following a pattern. Like, we know it's correlated, but we don't know if it's going to happen in the future.
Right, right. And that's where the engineers or the scientists come in. Another example is climate change. And one of the cool things is when I first taught this class, there was a huge group of people that did not believe in climate change. Okay. And that's because there wasn't much data out there. We're talking about the 1900s. You know, it was, I've been teaching a long time. And then as the years went by, all of a sudden the statistical significance made very clear that we were having climate change. In particular, we're having average global temperatures increasing. All right, so then the question is, what's the reason behind it? And there were a lot of different things that people looked at. One of them was maybe it was solar patterns. So maybe the sun was doing something in modern times, because that actually does happen. So then you have then you send a bunch of satellites up and you watch the sun for a while to see if it's doing anything. Does that make sense? And they found out it wasn't. And then you look to see what other big things have changed that might be a possibility. And one of the big things they found was carbon dioxide. And then they couldn't find anything else that would cause any problems. So that's why now it's been many, many years since, again, this research was started, we know that carbon dioxide is the reason, because a whole lot of science was done after that was a suspicion. But when it was just a suspicion, people didn't know yet. They hadn't done the science. So you use the statistics to help motivate the scientists to look into what the cause might be. Does that make some sense? And then science tells you the truth. Does that make sense?
Yes.
So
I guess it was.
so in this case, what they did is then they went and they realized the lake was getting worse. So then they looked at all kinds of things that could cause it to be worse. Weather's one of them, but our weather hasn't changed that much, from year to year since 1968. Has a little bit, but not that much. So they found out things that were changing in Tahoe, where there were a lot more people, and in particular, there was a lot more changing of the creeks. There was a lot more of construction going on with putting pavement down, stuff like that. And then they were able to figure out what the cause was, but based on the science. The statistics starts the worry about things, and then the science verifies it. Does that make sense?
That does make sense. So basically, well, in this example with the lake, the statistics didn't tell us that um, we would necessarily. Didn't tell us that next year for certain um, will have the average clarity decreased by the slope, but it did tell us that there was this problem, and then we used that information to investigate potential causes and then come up with a convincing argument on why this is causing this and how to take action against it. Is that basically how it's
Right.
being used?
Exactly. And let me show you. See, that's the next picture. So it's a perfect question you asked. So after Clinton and some Congress people came here, then they passed the law, because they did the UC Davis. These are scientists. I trust scientists. They did research to see what the causes might be. Again, regression analysis does not tell you cause. It tells you trends and tendencies. So they found out some of the causes. I won't get into all the details, but there are a lot of different things. And then they went and did something called BMPs, best management practices is what that's called, to try and bring things back to what nature was before 1968. And then they watched the numbers every year after they made all those changes. And here is, I don't know if you noticed, but before it stopped in the 1990s. Now it doesn't stop in the 1990s. Now we go all the way to 2020. There's a picture in 2020. What do you notice after Clinton was here to now? What do you see in the trends? If you look at this particular scatter plot and you ignore everything to the left of 2000 and you look to the right of 2000, what do you see? What do you notice about the scatter plot? Yeah, now it's stagnant. It still goes up and down, but there's not a downward trend in the depth of clarity, which really tells you it worked. Do you see? So the statistics basically helped us put out the big red flag. Then the scientists determined what was causing the problem, and then the politicians brought the money in to fix the problem. And then the statisticians looked at it again and said the problem's fixed. And that's what we want. We want the problem fixed. Any questions on that? So what it means, and by the way, problem fixed means we need to keep doing what we've been doing the last 22 years. Okay, so it doesn't mean we shouldn't use any money anymore, but we need to make sure that we keep doing the same thing. Any questions on this idea?
I just observed, and this is just me, like just looking at it. There's like seems to be oscillations between the years, like up and then down and up and then down.
Yep.
Like especially you can see this from like 2000 and later. It's like clearly has some sort of peaks.
Yep. And then you go and you look, see, okay, it's now since 2000, it's not the fact that, the years have been going on. Now it's ups and downs, right? So then you bring the scientists in and say, what's going on these peaks and valleys? And as I mentioned, it turns out what's been going on is these are big weather patterns. When you have things like this 30-meter, this low spot here, well, this high spot, I know it looks low, but this means high in terms of the number of meters. That's when we had a drought. If we don't have, it turns out if we don't have much precipitation, that's good for our lake. Whereas if we have a lot of precip, then you're gonna have a lot of runoff and our lake's gonna get less clear. And they were able to do that. And then they did, which I don't have the data with, on right here, but they were able to look at the data on, instead of year versus depth of clarity, they looked at the precipitation amount for that year versus depth of clarity, and also found a correlation. Does that make sense? And that's where the peaks and valleys are coming from post 2000, is they do another regression analysis with a different variable. And that works. And they found it was very predictive. Any questions on that idea? Okay. But here's one thing, is that doesn't mean that we can do anything about it. We can't say, we're going to do everything we can to make sure that we don't have any snow this year. Because, well, there's all kinds of problems with it. One is we don't know how to do that. And the other is it causes different problems if we could just get rid of all snow, even though it helps our lake clarity. So that one you just got to live with. So some things you have to live with, some things you can deal with. Man-made issues we can deal with. Okay, so that's kind of what that is. And this is the data, by the way. And in fact, if you go in, let me do that. Here's the data for that. So I'm going to go new plot and go there, copy that in. And let's copy these guys in. And plot points. Now we look at everything. And if you look at now R and R squared, now R is negative 0.41. Very different. Okay. There's still a kind of what sometimes you'll say a slight correlation, but nothing looks significant. R squared now is only 17%. So year is not the big predictor anymore. Do you see that? Our p-value is greater than 0.05. So there's not any statistically significant evidence that there is a correlation between year and depth clarity since the year 2000. Any questions on that? Okay, so again, this is the newest data instead of the older data. So a couple things is causation and correlation. Correlation does not allow you to use the word cause or anything like that. And I want to, most people don't even think about this, but the word because has the word cause in it. So it's also a very dangerous word to use in statistics. So do not use cause, do not use because when you're doing any regression analysis. Any questions on that? Any questions? Okay, the only time you can sometimes do it is if you have what's called a randomized control study, but that's too hard to explain and it's very complex and it's usually very difficult. And it's impossible with, for example, the depth of clarity example. Okay, the year is not the reason why clarity went down. It's because really, as years went by, there were more people here. That was the issue, was the people. Okay, instead, use words like tends and predict. Those are good words to use for regression analysis. Any questions on that? Okay, and by the way, when you have your exam on this week, and you're asked to do a regression analysis thing, I will take off points if I see words like cause or because. Okay. Another one that you should worry about is the word will. So it will happen. You can only predict it to happen. Do you see the difference? So those are some dangerous words. Okay, cause can only be used if you have the science behind it. That's really what you need. Statistics is not enough to show cause. And I think that's what you were asking is, but you can't say it's a cause thing, and you can't. But you can say there's a correlation. You can say we've had a tendency. Any questions at all on this idea? Okay, so it turns out we are not going to have a secret word. In this case, we're going to have a secret letter. Even easier. So the secret, the answer to the secret word quiz for this week is R, because R is the correlation, and it's very important for regression analysis. So the secret word will be R. Okay, lowercase is best. You didn't know this was a private class? A pirate. Oh, R.
Because R.
Sorry, I didn't get that right away. Okay, yeah. But this R is talking about correlation, not the R. So that's pretty much it for today. I want to remind you again, please make progress on your project. I'm going to give you a heads up. Your project is due on I believe it's the 11th. And I am going to be mostly off grid on the 10th and 11th. Okay, I'm going to be at a conference, and I'm one of the board members, and I'm help running this math conference. And a big part of it is statistics, by the way. It's a statewide conference. So I will be mostly off grid. So if you have questions, they need to be really asked by really that Thursday. Okay, in fact, I'm leaving on Thursday. So I might have a little internet time to look, but not much. So I want to give you that big heads up. The last couple of days, I won't be there much to help out. Maybe, I don't know, Braulio, if your schedule is good those last couple days. Huh?
It looks like I have I'm working on the 11th that afternoon.
Uh-huh.
For any last few questions that you want to ask.
Good. So
But feel free to email me ahead of time so I can review and kind of save you some time.
Great. So the person to ask will not be me actually on the very last possible day. It'll be Braulio, because I'll be helping running a conference, and it turns out I'm the AV specialist. So I'm in charge of all the technology for the conference, which means there could be big headaches because you never know. Hopefully you know that computers can die on you. And the connection to the speakers and the projector and all that kind of stuff. So that's my job, and I got to be there every moment for that. So I want to give you a heads up, but I'm going to be around a lot until the 8th of December, to help you out. So I think I'm going to stop the project. Get there. I'm going to stop the recording.